good evening, and welcome to the Tech Forward series, the first of the Tech Forward series. So this now we've been Triple IT has been here for across 25 years, completing 26 years, and we are the center of the IT world, or geographically at least. And we have had very good relation with many of the companies, but they are all on and off. There are some projects we get, or we conduct some courses, etc. But the idea that you know really came about after Professor Ashok Jhunjhunwala of IIT Madras took over as our chairperson about 6 months or 8 months ago. He said, there's no other institute in the country, the top institute in the country has this advantage of being in the middle of so many IT institutions. You should connect very strongly with the IT companies or IT professionals, etc. And one of the things that we thought of is have a series of events, monthly events, where some really current technology or trend is in focus, and it has to be truly industry and academia. Now, us professors standing up and talking endlessly about things is very common. That will bore everybody. Should not be just that view, but it's same topic or same area, same subject. How do you approach from academia as well as from industry? What are the challenges? What are the pitfalls? What are the big opportunities ahead? This is the idea, and the invitees or the audience should be the entire industry, academia, whoever else. So this is we've been working on it for over 6 months now, designing it. It's so hard to get off the ground, and because the worry is, in fact, it's much easier to get off the ground than to sustain it for long. So we've been working out at least 3-4 months. Next 3-4 months is worked out, and I'm so glad and thankful to Qualcomm and Shashi for being a ready host for this one. We worked very closely with each other, and I'm told when they came, we had a Qualcomm day in Triple IT just before, just in September or so, last September, and I was amazed to see the number of our alumni working in Qualcomm right here. So I had to hear from them, not from the alumni. They don't come and visit us often enough to know that. So we have, and Qualcomm is a really high-end technology company. It is everybody knows about them as a communication hardware company, but now all these the boundary between hardware, software, everything is merging. And today's topic is a very good example of highlighting that part. So thanks. I thank the host for providing this opportunity, and let's have the first one and many more. And I also thank Ramesh and Sunori and all have been able to get I don't know, partnership from Times Group, and so we have people from there also. So let's see, this is a unique attempt in the country for sure of academia and industry coming together and highlighting some of the areas on a monthly basis. Let's hope what edition of it. So thank you for hosting this, and let's have the first one.
Thanks, Vijay. Thank you very much, and good evening, everyone, and very, very warm welcome to Qualcomm facility. And it's a privilege to host the first edition. Anything you remember after maybe few years, and I hope this will be a very successful venture or a successful attempt in bringing in industry and academia together. And if you remember back, I think you would all remember that we started off in Qualcomm. That would be great. So it's in a way kind of selfish. Actually, it's a. I think it's great that we had this meeting in Triple IT a few months back, and they were just kind of brainstorming across what we can do. I know there are lots of small initiatives, not just hiring, but some projects, some kind of things we work with professors, but there was no streamlining, and also more about knowledge sharing, what's happening on the academia, what's happening on the industry. Obviously, when you talk about industry, it's about execution, getting things out. How do you make money? from Qualcomm and Triple IT, and we will take it from there. Thank you so much for coming down.
Thank you, PJN and Sashi. Yeah, like I think a job well begun is, I think, job half done, and we will work on the other half to make it. We'll come back in 18 months, Sashi. We will do it here again. We'll do the 18th edition again back in Qualcomm. I'm sure we'll keep it going till then. So one important part of this was, I mean, like PJN said, the reason he told something like this, we got a council together. We'll introduce the council a little later. We got a steering council together. Sashi is part of the council as well. And but we also said each edition needs to have a chair so that there can be some deeper thought, because only two talks, and we're going to have a dispatch, a feature publication that comes following this, and there'll be three or four more features that will introduce the dispatch a little later. But we thought for each edition we needed to have a chair, a senior person that is chairing that particular edition, thinking about the talks, the topics, curating the talks, curating the features. So the first edition, we're happy to have Rajiv Parunkar, Vice President of Qualcomm, as the chair. So request Rajiv to come just set his thoughts and context for the two talks today and the dispatch features. Rajiv?
Okay, warm welcome to everyone from Qualcomm side. So today's talks, I think they are exciting talks from two of the prominent people from industry as well as academia. I think all of us are very well aware of what's happening in the world of AI. The last 1.5 years has seen a tremendous momentum on AI, especially generative AI. The focus so far has been on training aspect on the server side, where billions of parameters are getting used to come up with these large language models. What we expect to see in next months and years to come is how to utilize this power of AI on the edge, on the devices which we use every day, such as the phones or the laptops or cars and things like that. So today's talk is focused on that, AI on the edge. I think it will be an exciting talk in that journey to see where we are and where we are going from an industry perspective and as well as from an academia perspective. We are going to go through these seminars one after the other. So Rajesh will cover first from the industry perspective, followed by Professor Anup from Triple IT from academia perspective, and then we'll take questions from the audience here, live audience. We also have a live YouTube streaming ongoing. So we will take questions from the YouTube streaming as well. So any of the folks watching us live on YouTube, feel free to put your questions on the chat and we will take those as the time permits. So with that, I think without wasting too much time, I would like to invite the first speaker, Rajesh Narayanan, here on the stage to start with his seminar. Thank you.
The pointer. Check, yeah. Welcome everyone. Really happy to be a part of this series and part of the overall program today on the AI. And welcome to everybody from the Qualcomm side. Welcome to folks that are here, and welcome to people that are actually watching this online through the streaming link. And with that said, I'll actually get started. I'm Rajesh, as it says here. I actually lead what we call as the Application Technology Software Group here in Qualcomm, India, Hyderabad. And I'll be talking about what Qualcomm is actually doing to enable AI at the edge. What are the kind of challenges that we had to circumvent? And in terms of the hardware, software, algorithms, what are the key use cases based on AI? And also talk about what exactly is happening with Gen AI. How are we enabling LLMs on the Qualcomm devices? and essentially end the talk with what we have launched very recently called as AI Hub that actually enables developers to make use of our platform and actually deploy the models on our device. So with that said, I'll actually get started. So making machines a lot more smarter, lot more intelligent has been a vision. And Qualcomm has been working on this for over a decade in the context of AI. So as shown here, we interact with a lot of devices in our everyday life. Obviously, starting with your smartphone, smartwatches, a lot of the wearables devices, and then devices that are part of your home automation, devices that are there in your car. And when it comes to industrial IoT, the plenty of cameras, surveillance cameras, IP cameras, drones, and all of these devices are becoming a lot more powerful. They have a lot more processing capability in them. In addition to these devices have plenty of sensors that are actually collecting a lot of data about the surrounding, data about the environment, about the region that you are in. And essentially what you would like to do is process the data on the device, given that the device has a lot of processing capability, and kind of bring in a very context-aware, customized user experience, so which can actually lead to a lot better day-to-day life for all of us. And we are already seeing that with a lot of the AI-based use cases getting enabled on your mobile devices, a lot of the devices that have been coming out of the last few years, right? Starting with the always sensing camera, always on displays, be it voice activation and audio-related processing, a lot of these use cases that actually make use of AI. And like I said, yeah, plenty of use cases. So essentially AI, several of you probably know it, started off just as something very specific to image processing, right, based on all of the convolutional neural networks. But over the last 4 or 5 years, that has evolved. We use AI pretty extensively for a lot of the, not just image processing, but you use it for text processing, for voice, and several other use cases that have essentially exploded based on AI. And you can just kind of look at the examples. Obviously, a lot of use cases, pretty much everybody has a smartphone these days. And around smart homes, a lot of the products actually make use of AI, essentially with smart homes. And then things as part of your productivity, things as part of your entertainment, right? Video conferencing, the TVs that you actually watch, and a lot of the more upcoming technologies related to ADAS and autonomous driving, extended reality. These are all use cases. And specifically when it comes to industrial IoT, use cases around video monitoring, surveillance, a lot of these use cases essentially make use of AI. And one of the key things that I've actually called out in the slide, for this AI to be super successful on the device, what you need is really be able to build an intelligent and a personalized experience. And the need for this, the demand for this is growing. And what you really want these devices to do is kind of exhibit, show a human-like experience, right? Essentially where these devices respond to queries like how a human would do. And for all of this to actually become a reality, you really need very powerful AI engines to be running to get enabled. So with that said, with the advantages and the kind of use cases that AI is enabling, I'll specifically talk about why on-device AI. You could do AI on the cloud, you could do AI on the device. So I'll talk about why exactly on-device AI, what are the kind of advantages that it brings. First and foremost, personalization. So like I said, essentially, you are collecting a lot of data from the sensors that are there on the device, which are collecting data regarding the surrounding and the environment that you're in. And all of this essentially can bring in a very personalized experience to the end user. So obviously, a personalization is one of the key selling points for on-device AI. And obviously, all the data that you're collecting, right? Data that you're collecting with respect to the user, it's obviously there's a lot to send it over to the cloud. So obviously, privacy and security is another aspect. And with the talk of global warming, all of us, clearly see that with the temperatures kind of going up. So obviously, what you want to do is kind of keep the overall energy consumption a lot low. A lot more optimal and in terms of their power consumption actually going down. So on-device AI, purely from an energy consumption standpoint, is going to be a lot lower compared to running things on a much bigger infrastructure, say, be it the cloud. And the fourth key aspect where on-device AI has its own advantages is with respect to performance. I mean, think of the use cases that you enable, let's say ADAS, let's say XR. These are use cases that have extremely low latency. For example, your voice activation, you say, hey, Alexa, you really want the device to respond like in a second. If the query were to go to the cloud and come back, obviously you're dealing with a lot higher latencies. So essentially, when you talk about performance, you're talking about a lot of the low latency use cases, and with the performance capability that is actually being enabled on the devices. So this is really becoming possible. And last but not the least, the cost. So with the on-device AI, it's a lot more affordable compared to actually doing it on the cloud. And in the subsequent slides, I'll talk about with the transition from traditional AI to Gen AI, how the cost per query is actually going up and how cloud economics isn't going to work, right, compared to doing it on the device. So with that said, with AI, we kind of talked about, hey, why exactly AI is key. I kind of talked about establish the need for on-device AI. And then I'll get into what exactly Qualcomm is doing to enable on-device AI and the industry as a whole. So like I said, I think one of the key things is you really need to, for AI to be pervasive, you really need your overall solution to be extremely power efficient, at the same time bringing in the kind of desired performance that is actually needed. So with that said, so what Qualcomm essentially has done is we've been working on AI for over a decade right now, and we had to get past a lot of hurdles to make this a reality, to start enabling use cases. So first and the foremost, yeah, obviously a lot of design and architectural work around building very efficient hardware. I think one of the key aspects, considering the diverse kind of workloads that are there, you need to have heterogeneous hardware. So one hardware isn't going to be able to enable all the kind of AI use cases. So essentially build heterogeneous hardware and all of the algorithmic advancements that are needed. So if you look at it, I think one of the key aspects when it actually comes to your devices on the edge, these devices have very low memory footprint. And obviously, power is going to be one of the key concerns on your mobile. Nobody wants your mobile to actually discharge like within like 15, 20 minutes. You really want your device to actually be usable all day long. So you had to bring in a lot of algorithmic related advancements to enable AI on the edge. And last but not the least, software and tools. As a developer, how do you actually take your model that you have actually trained and how do you deploy it on the device to kind of enable the use cases that I talked about? So essentially from the Qualcomm side, so we worked on these for over a decade, and I'll kind of get into each of these aspects. So the efficient hardware, like I said, a single piece of hardware, we strongly feel a single piece of hardware isn't going to be able to enable the different kind of use cases that you're dealing with on the AI side. Some use cases are on demand, some are pervasive, some are sustained use cases. So depending on the type of use cases, we have different types of accelerators. Traditionally, AI has always been using the CPU. And we have powerful CPUs. The performance of these CPUs has been going up generation over generation. And CPUs essentially are suitable for sequential control, suitable for low latency kind of workloads. For example, like your gaming kind of use cases. And then we have the GPU. GPU essentially is very well suited for image processing, where you really need high precision, high accuracy. So we have the GPU as well. And then last but not the least, we have what is our custom accelerator, our hexagon processor. Essentially, we call it the NSP. It's the neural signal processor. So the NSP essentially is our custom hardware that actually allows you to enable plenty of use cases at peak performance at extremely low power. So we'll actually talk about our NSP and what exactly we've been doing on the NSP, both with respect to traditional AI and more recently with respect to Gen AI. And as a developer, as somebody who's actually enabling your use case, you could choose one of these accelerators really dependent on a lot of these factors, right? You could actually use the CPU or the GPU. For example, yeah, what kind of use case? If it is an imaging kind of use case, perhaps, yeah, you would want to look at the NSP or the GPU. But if you are looking at, hey, a sustained use case, a use case that runs for a very long time, and obviously, like I said, on device, power is a major concern. So you would probably look at the NSP. And it also depends on the device type, because if you look at it, you have devices that are very expensive. You have a lot of cheap devices. Depending on the type of the device that you're using, you may have one or all of these accelerators. So obviously, that is is one. And then the overall development time. As a developer, right, you probably have your model that's actually working somewhere. You want to take that and actually deploy it on one of these platforms. So obviously, it's your development time and your developer expertise. Maybe if you're more comfortable with the CPU, you can take your model, deploy it on the CPU. And last but not the least, the overall KPI, right, in terms of the performance that you actually need. Depending on the performance, each of these accelerators have their own uniqueness. Depending on the your performance needs, you could actually pick one of them. So like I said, yeah, this essentially is our AI engine. So it has these three accelerators. The code name for our GPU, it's called the Adreno. And generation over generation, we have been increasing its performance. We've been increasing its capability. And then I'll get to the NPU towards the end. Then we have our Cryo CPU. So yeah, and the more recent one, essentially, we also have the Orion CPUs. So the CPU, in terms of the overall CPU's performance, in terms of its capability, efficiency, that essentially we've been working on it. And this has been going up generation over generation. And last but not the least, yeah, it's our Hexagon NPU. So this is our custom accelerator, and I'll get to it in a bit in the subsequent slides. And obviously, all the edge devices have a huge amount of memory. And essentially, what you do is, while yes, yeah, it is huge in the more recent days, but compared to your PCs and others, yeah, it's a lot smaller. But essentially, yeah, we have the whole memory subsystem, which can actually where you actually place your models, and essentially you fetch data from their process and actually push it back. And all of these essentially process data that actually comes from our sensing hub. The sensing hub is where essentially we have our camera sensors, we have the other sensors related to, let's say, your gyro and all the other, or related to audio. So we have the sensing hub. So the data essentially comes into the sensing hub from all of the other sensors that you have on your device. And once the data comes through, you could actually have the models work on them depending on, or making use of one of these accelerators. So like I said, yeah, so I'll kind of get into a bit into our NSP, which is our custom the neural signal processor. And essentially, it has a fused AI. It's a fused AI accelerator. So traditionally, Qualcomm has been using the signal processor starting with the modem. Post that, we used it for image processing, a lot of the audio processing, and based on all of the R&D that we have done, based on the work that we've been doing for over a decade on AI, we've been able to bring in a lot more improvements, a lot more architectural enhancements to our engine. So what essentially started off as a very simple signal processor that was suited for image and audio processing, that's been enhanced for AI-related processing. Like you said, like shown here, we have a scalar engine. And then we have a vector engine that essentially was used for a lot of the image-related processing, a lot of enhancements that have gone into our vector engine. And more recently, for AI workloads, essentially we have added the tensors. So essentially, these are the three key accelerators that we have on our NSP. And obviously, we have large shared memory. And what this actually enables you to do is, depending on the kind of processing that you're doing, you could actually take your data, let's say, that is processed by your vector engine. It could actually be channeled through this large shared memory and picked up by your tensor for any subsequent processing. Without that, what would essentially happen is the data actually goes to your memory, and then you got to read it back from your DDR subsystem. Like I said, one of the key things for when it comes to edge AI is actually power. So you really want to keep the power consumption really low. So the large shared memory really enables you to do it, because you are processing the data and actually channeling it between these accelerators without really going to your external memory. So this has been one of our key additions for actually enabling a lot of the AI workloads, and more improvements, enhancements have actually gone into this to enable Gen AI kind of use cases. I'll actually touch on that in the subsequent slides. And yeah, so I kind of talked about the three hurdles that we had to get through. The first and the foremost, I just talked about the improvements in the overall hardware. The second aspect is the kind of work that we actually had to do to bring in optimized algorithms that could actually run on the device. And that really meant coming up with a vision, right? Having a problem statement, coming up with a vision, and essentially acting on it and coming up with a solution that actually can translate your vision into something that is realizable on the device. To that effect, essentially, as part of the Qualcomm R&D, typically what we do, I mean, most companies, that do R&D kind of work, essentially do this. You have a vision, identify a problem statement. Once you have a problem statement identified, as a next step, you really look at what are the methods, what are the state-of-the-art techniques that you can actually come up with to take care of the requirements specific to the problem that you're trying to address. And in the case of the AI, obviously, we had to come up with a lot of the quantization techniques. We had to bring in a lot of optimizations so that essentially your device, your models can actually be deployed on the device, and the device that has a lot lower memory footprint. So what are the kind of quantization and optimization techniques that you actually bring in without really losing the accuracy? And then once you have that, you need the entire software stack. So you can essentially deploy something on the device and actually get it to run. And as a part of that, essentially we do a proof of concept, which helps you actually demonstrate something and helps you iron out whatever kinks that you may have with your solution. And once you get through that, the most important step towards the very end is essentially commercializing your product, as a part of which you work with the entire ecosystem to roll out your solution. And once that is done, whatever learnings that actually come from that, you feed it in and start your next cycle. So this is essentially how you've been working on. And this is the kind of stuff that has actually enabled us to really work on the improvements to our signal processor, which eventually ended up becoming our NSP, and also all of the improvements, enhancements that we've been bringing into our software stack. And based on just to kind of touch upon some of the work that we have done to enable AI on the edge. Just an example, typically you have a trained model. It has multiple layers. And once you could take the model and actually deploy it on the device right away. But like I said, one of the key challenges getting to run your AI model on the device is primarily around the overall memory footprint and, like I said, power. So what you essentially have to do is you got to compress your model and essentially prune. Maybe you're removing some of the layers, but at the same time, you got to do this without really compromising on the overall accuracy. And then you can actually do a lot of quantization. Maybe the model that you have maybe is float. You quantize it. Maybe you quantize it to in 32, in 16. So that also reduces the size of the model, and this essentially helps you fit in the model on your edge devices, where the memory footprint is a lot lower compared to, let's say, like a PC. And then last but not the least, once you have the model that's kind of quantized, you actually take it, actually run it through the offline tools. So essentially that can actually translate your model so that it can be deployed on one of the accelerators that I talked about in the earlier slides, right? Be it the CPU, NPU, or the GPU. So if you look at it, our AI research essentially has been focused on increasing the overall power efficiency, at the same time bringing in the desired performance, right, that is needed for you to enable very compelling use cases on the edge. And out of our research, I think one of the things that I want to talk about, it's an open source project. You can look it up. It's online, AI Met, which is our AI model efficiency toolkit. And what this essentially does, like I said, you have a trained model, and which is based on one of the popular frameworks like TensorFlow or PyTorch. You have one of those models. You essentially have to take that model and deploy it on the device. Prior to that, you can actually run it through AI Met that can actually compress and quantize the model. Like I said, compression essentially reduces the overall size, and quantization again, helps in the overall size reduction, but at the same time without really compromising on the accuracy of the model. And once you have the optimized model, you can actually take it and deploy it on the device to enable a plethora of use cases. So essentially, AI Met is one of the things that actually came out as part of our overall AI research. So like I said, so essentially I've talked about hardware, I've talked about the research that we actually do. And then last but not the least, it's essentially the software stack, right? Because you need the full stack for the end user to be able to take a model and actually deploy it. So what we did essentially is like a few years ago, all the tools essentially that we offer as part of enabling AI on the edge device, essentially we clubbed it under what is called as a Qualcomm AI stack. So like shown here, it supports all the different frameworks, like be it PyTorch, TensorFlow, Onyx. It supports a lot of those. And the Qualcomm AI Engine Direct, which is essentially the entire product, essentially is a suite of compilers. It's a suite of the entire software stack that actually enables you to accelerate your model on one of the accelerators, like the CPU or the GPU or the NPU. It also has a lot of the debuggers that actually go with it. It has the profilers, because as a developer, as someone that is actually taking the model and deploying it on the device, you need to be able to profile and really look for, hey, what is the kind of performance that I'm actually getting on the device? So essentially we have the profilers, and as you're deploying the model, obviously you want to be able to debug things as a developer. Yeah, something doesn't work as expected. Yeah, you want to be able to debug. And the lowest layer essentially is the software that comes as part of the SoC. Essentially is a lot of the drivers that actually enables you to deploy the model on one of these accelerators. And the last row essentially shows all the different operating systems that we actually support: Android, Windows, Linux, Ubuntu, CentOS, QNX. So what Qualcomm believes in is, as a developer, you should be able to develop once, but deploy anywhere. And if you clearly look at it as someone that's actually trying to deploy your AI model using our software stack, you should be able to take your solution, deploy it across any of these platforms that actually ranges from your mobile device to your, could be your cars, it could be your IoT devices, it could be XR. So essentially, that's our overall philosophy and the approach. So like I said, essentially, that is the work that Qualcomm has been doing. I kind of talked about what we have done on the hardware, what we do with respect to the overall research, and what we have done with respect to software to actually make on-device AI a reality, right? And enable plenty of use cases partnering with the ecosystem. So obviously, over the last couple of years, Gen AI has taken off in a very big way. And the challenges with Gen AI is the number of parameters that you need to support. So like shown here, depending on the type of model that you're dealing with, whether it's a to image or models around image understanding, video understanding, the number of parameters that these models support range anywhere from a few million to hundreds of billions. And one of the key challenges that we see is, how do you really take these large models and deploy it on these small edge devices where memory is a premium and where you got to make sure that the device runs at extremely low power. So what we actually think is, with the capability, with the AI capability that is actually there in the billions of devices that are out there, the edge devices that are there, they are very well positioned to enable generative AI on a lot of these devices, because, like I said, a lot of the devices have the AI capability. You need to be able to tap into that capability to make a Gen AI a reality. But then there are certain challenges that we really have to address as generational improvement in both the hardware and the software. So, like I said, one other reason when it really comes to, as we are transitioning from traditional AI to generative AI, one of the key challenges is going to be the overall cost. And as you can see here, the cost per query is going up almost about 10x as you are making this transition. And you can just do the math with the number of Gen AI applications that are there and the billions of users that are there. So cloud economics isn't going to be really viable when you're talking about cloud to do large language models compared to doing it on the edge. So with that said, I'll talk about the generative AI trends, right? Perhaps, yeah, several of you are using a lot of these use cases, but probably aren't aware that the brain behind this whole thing is generative AI. So a lot of, on your mobiles, essentially, you're able to do a lot of text-based processing, right? Text to image, text to voice, a lot of those use cases. And stable diffusion, very good example, right? Essentially, text to image. And then a lot of the productivity use cases on your laptop. For example, with your Teams calls, after meetings, being able to generate meeting minutes, being able to identify AIs. Essentially, that is another big use case with generative AI. And a lot of use cases around speech, around audio. I mean, yeah, there are just a plethora of use cases. So obviously, with Gen AI, I think we are seeing the explosion with respect to the overall LLMs, right? And like I talked about in the previous slide, the number of parameters that we support. And we are also seeing in terms of the lot of multimodal models, right? Because these are not just the large language models, but multimodal models, which essentially can take inputs from multiple sensors. So it could be taking inputs from your audio, it could be taking inputs from your camera, it could be text, and essentially it can process all of these together to bring in a very context-aware experience. So we are actually starting to see that. And the other thing that we are also seeing is the smaller models, it doesn't necessarily have to be models that are billions of parameters. Smaller models we see are also becoming extremely capable. So when we talk about Gen AI, I think I talked about how Qualcomm has been working on enabling traditional AI until about a few years ago. But then when we talk about Gen AI, there are newer set of challenges because these models are pretty big. So obviously you need support for huge compute. That is one. And given the size of these models, I talked about the number of billions of parameters that they are dealing with. So essentially there's need for huge bandwidth and a huge memory so that you can have sustained performance, because a lot of these models essentially need to support a certain number of tokens per second so that the end user experience is really very compelling. So all of these really translate to some unique hardware challenges. And obviously when it comes to the software, like I said, yeah, these models have very huge memory needs. And for the software essentially to do the memory management, right, of your device, because on device memory is a premium. So your enhancements that are actually needed in the software to take care of the memory management. Last but not the least, yeah, the improvements that are needed in the algorithms, right, with respect to the regulatory compliance, making sure these algorithms are not biased and take care of the other challenges like hallucination and things like that. So essentially, Gen AI, the transition to Gen AI has brought in its own set of challenges with respect to enabling this on the device. So I'll talk about some improvements that we have made, and obviously these are generational improvements that are actually being worked on that will get rolled out in the subsequent years. So I talked about in the previous slide, I talked about our NSP, our neural signal processor, has 3 accelerators, the scalar, vector, and the tensors that are kind of suitable, that are used for a lot of your ML workloads. So in addition to that, so obviously our tensors to support the Gen AI models, we have increased their overall peak performance. So you can clearly see that, right, in terms of the peak performance of the tensors. We also clock each of our vector engines, we actually clock them higher. So by clocking them higher, essentially you are able to meet higher performance, you are able to meet higher throughput, and kind of essentially get to the tokens per second that is actually needed to enable compelling use cases on the device. And then the last but not the least, yeah, the increase in the overall bandwidth and the throughput. Yeah, and just speaking of the large language models and the size of the parameters. So with the improvements that we are seeing on the device with regards to enabling large language models on the device. So we are actually seeing more and more of the large language models essentially moving from the cloud to the edge. And this kind of depicts that. And if you look at it on our Snapdragon platforms, if you look at the models that we support, models that range anywhere from about 10 to 13 billion parameters. So these are all the models, different models from Microsoft, the Llama models, the OpenAI Whisper models. So essentially, we are able to actually support multiple billion parameters, right? Models that require multiple billions on our devices with all of the improvements that we have been making to our hardware and the software. Yeah, I think I'll just quickly touch upon a few use cases. Yeah, like the smartphone based on the Gen AI. Essentially, your smartphone essentially is becoming a true digital assistant. I think this is a very good example. You could use your phone to say, hey, can you just draft an email to this person? And it's kind of and kind of provide the context. It can quickly come up with the email. And then XR is one of the new upcoming technologies. So if you look at it, Gen AI specifically can actually create a very immersive experience as shown in this example through a voice prompt. You could say, hey, create a 3D model of a car, and Gen AI can actually do it on your XR devices. And it can also bring in the personalized themes, right? Can bring in the contextualization, can bring in the customization based on the user and based on the user's preference. So again, yeah, this is another use case. And then specifically specifically on the PC, plenty of use cases around productivity on your PC. Like I said, yeah, Teams call. After a Teams call, you could actually use Gen AI to generate the meeting minutes. You could use it to identify the action items. Plenty of use cases, and especially with the launch of the new Copilot based Microsoft, the Windows devices that just got launched 2-3 days ago. A lot of use cases based on Copilot that's actually getting enabled around productivity. And yeah, like I said, yeah, use cases around multi-language transcription and translation when you're actually on a voice call. You could have different folks, right? I mean, speaking in their own languages, and then yeah, you could essentially do the translation. So Gen AI is actually making this possible on your PCs. And yeah, and a lot of use cases within your industrial IoT. Just as an example here, yeah, based on how the customers actually come into your store, you could actually look for that data and essentially come up with use case based on AI. You could actually come up with use cases that can actually suggest how your store layout should look like. Really looking at how the customers actually move around on the shop floor. And automotive, again, yeah, a lot of use cases around automotive that can actually improve the overall drive policy. So like I said, essentially Gen AI has been able to enable plenty of use cases across several different segments. And yeah, and this kind of gives you an overall summary on all the different segments, right? I talked about mobile. You can look at the number of use cases around image processing, use cases around audio. And when it comes to AR, VR, a lot of the use cases around hand tracking, body tracking, and then 3D reconstruction, use cases on the IoT and camera with regard to face detect, multi-object detect, video summarization, and there are plenty more use cases. These are just some small snippets, and then things around IoT and ADAS and AD. So essentially, these are the kind of use cases, kind of gives you an overall idea of the number of end user scenarios that are getting enabled with Gen AI on device. And one of the key things that we have been able to do at Qualcomm is with our one technology roadmap. I talked about all the different accelerators that we have. So essentially with our accelerators, this actually scales across all the different business segments. You can actually see it starting all the way from automotive to earbuds. So our solution can actually scale across all these different segments. And like I said, yeah, this really enables you to kind of develop once and deploy it anywhere. So that one of the key ingredients behind that is our overall one technology roadmap that actually scales across multiple segments. So I'll just talk about a few examples, right, based on things that we have worked with our partners that actually showcases the kind of use cases that we have actually enabled on device. Yeah, this is just an AI assistant based on the Skyscanner plugin, and this is actually running on our Snapdragon platform. And you can see
Can you show me flights between San Diego and New York departing on December 1st?
Here is the travel plan for your destination.
Can you add 2 adults to that plan?
Here is the modified plan.
Can you change the departure date to December 15th?
Here is the modified plan.
Okay, submit that.
Okay, I will send your plan to the travel website. Here are your booking options.
The use case actually running on our Snapdragon platform. Then I'll just one other use case. This happens to us all the time. Nice picture, and then yeah, somebody photo bombs. So you can look at what it actually enables. Oh yeah, so hopefully you could relate to it. I mean, things that we deal with all the time, right? Yeah, so I'm really coming to the end of my presentation. I think I'm slightly over. So yeah, so I think one of the key things that we talked about is all the technology that is there. Now, what really matters is as a developer as someone that wants to take the model and actually deploy, how do we really enable it on the Snapdragon platform? So we essentially launched Qualcomm AI Hub February of this year, hardly 4-5 months. A lot more improvements, enhancements are actually going in. This was actually launched with the developer focus. Essentially, we have this philosophy of developer first, where we really look at improving the overall user experience for the end user when they actually take their model and deploy. So essentially, you can look it up. It's aihub.qualcomm.com. Essentially, it's a single repo that has all the data, all the documentation, all the tools that's actually necessary for you to take your model and run it. Also with a lot of the targets and devices where you can actually take the model and actually deploy. So I'll just quickly run through how as an end user, someone that wants to actually use the Qualcomm platform, how does your journey really look like? You could actually go to this website. Essentially, you could pick a model. We have about 45 plus models that are actually pre-trained, that are highly optimized. You could pick your model, or you could build your own model. And bring your own model. So once you have that model, you can actually pick one of our devices. Like shown here, we have plenty of devices. So you could actually pick one of the chipsets where you want to run the model. And then you could pick your runtime. Like I said, we have multiple runtimes, CPU, GPU, NPU. You could pick where exactly you want to run your model. And once that is done, within about 5 minutes, you should be able to really test and validate the model on the device and then tune based on your needs. And once that is done, then as someone that's actually developing the model, you can go deploy it on the final edge end user devices. So essentially, this is something that we have actually enabled starting February, and it's available for anyone to go make use of. Like I said, the Qualcomm AI Hub right now, it supports 100 plus pre-optimized models. We are adding a lot more, and you could also bring your own models. And then one of the key aspects here is, once you have a model, you want to actually deploy it on a device, you could either have your own device, or you could have the cloud-hosted device that Qualcomm actually provides. So you could actually pick one of these devices and actually run your model without really having one on your own. And last but not the least, as a developer, you should be able to do this in less than 5 minutes with about 5 to 10 lines of code. So this is something that we have actually rolled out very recently, and bringing in a lot more improvements and enhancements. And this is my closing slide. Like I said, essentially, we've been doing a lot of work, right, to advance AI, to actually democratize AI and to make AI ubiquitous. And as part of all of the research work, essentially bringing in a lot of innovation, a lot of improvements to our hardware, to our software, and with a lot of focus with respect to the overall power, at the same time ensuring we have the right kind of performance. So with that, I actually finished my presentation. Hopefully, this was pretty insightful and something that you learned from with respect to what Qualcomm is doing. Okay, thank you.
Thank you, Rajesh. Thank you for the insightful presentation. I hope all of you got a glimpse of where AI is today in terms of the industry, as well as what Qualcomm is doing in that regard. And feel free to look into the websites aihub.qualcomm.com for any help or anything that you need to know more. With that, I think I will call Professor Anup to the stage for the second part of the presentation. We will take Q&As at the end after both of these presentations are done. So please hold on to your questions till that time. Thank you.
Hello. Am I audible? I hope so. Okay. Good evening once again. So you listen to the high level view of what is happening in the industry through Qualcomm, which is actually involved in almost every aspect of AI and on the edge. But my talk would be far more specific. We are going to talk about, first of all, only computer vision, which is one small portion of the whole AI story. And because it's a research talk, I'll be telling the story from my viewpoint, which means it will be mostly based on my own research, even though a lot of work is happening in our lab, not just from me, but there are a whole bunch of other researchers in my lab itself who are doing very exciting things. I might refer to some of them later, but won't dwell too much on it. And I had to put a customary generative AI image which would say, what does AI think about vision on the edge? So somebody looking, sitting on the cliff edge and looking down, having a vision of what is going ahead, just what AI would think about it. So essentially, I'm talking about the interplay between these three aspects. One is computer vision, second is AI, and the third is the edge devices. Okay, this is not new. A lot of work has happened even before the current hype in Gen AI, even before that, the AI and vision hype, even much before that, there have been several devices which were in place, which would do things like defect detection, for example. In a factory, when objects are produced, how to do defect detection, this work has been going on since decades. And especially with specific sensors like ultrasonic sensors and so on, X-ray devices. A lot of work has happened. We all use our mobile phone unlock either through a fingerprint or face. There is AI going on the edge in that case. We all walk through airport security. Almost all cases, it's not just the person who is looking at the devices. There is an AI which is looking at it and marking out potential dangerous things out in the X-ray images. Of course, all of us use QR code, which is doing some level of minimal computer vision on the edge, license plate recognition for toll gates and stuff like that. So you've seen applications like this even before the latest AI machines, algorithms. But this edge has moved forward now with far more compelling use cases with modern AI coming into the picture. So autonomous navigation is, of course, the big story that is always coming next year, 3 years from now, whenever it is. It's always, just around the corner. So that's one area that we also have been working in our labs in terms of using computer vision to understand what is happening on the road, to understand, things like, can you detect people who are riding? Here's an example of a camera that is placed on the dashboard, which is detecting people running, triples. That's traffic violation. You're not supposed to have 3 people on the motorbike. You wouldn't think so by looking at Hyderabad traffic, or people who are not wearing helmets and so on. So there may be several use cases where if you have AI deployed on the edge, which can detect and possibly persuade the drivers to drive in a better way. We have technologies developed which look inside the car and monitor the driver and try to look for connections between how they drive, what are the relationship between that and behavior on the road, and so on and so forth. We have all seen devices becoming more intelligent through cameras. Things like the Amazon Echo has now a version which has got a camera built into it. One of my colleagues, Makrant, is also working on trying to use a basic smartphone as as a medical device for basic diagnosis for children, for infants, and so on. So a lot of interesting work going on in this space now that more powerful AI algorithms are available. A lot of powerful use cases are being enabled. So that's the high-level story. So I would like to now try to put the 3 things together and set the context for my talk. These 3 items, computer vision, AI, and edge, they play together. Of course, one way to think about it is that computer vision has been pushing the cutting edge of AI. And this is definitely true, that most of the big jumps that has happened in the recent years in the AI, starting with CNNs, the convolutional neural networks, came out as a result of trying to process images efficiently with neural networks. Generative AI, there has been a lot of input from the computer vision community in it. Foundational models, which essentially go beyond just languages, but try to incorporate multimodal models that Rajesh talked about before. And in future, we are expecting that at some point we will get to artificial general intelligence, and at that point, it has to be strongly influenced by vision and 3D understanding of the world. So this computer vision would play a big role in it, but that's not the edge we are talking about. That's just the cutting edge of research. So I'll just leave it at that. We would move to what innovations in vision is allowing to put AI on the edge. Okay, so what computer vision is doing so that vision algorithms on the edge are becoming possible. So that's one kind of area that I would like to talk about. The second is what improvements in AI is helping to push computer vision to the edge. So there have been improvements in computer vision that allows it. There have been improvements in the AI which allows it. So those are two important things that I would like to talk about. The third aspect, of course, is improvements on the edge, which is allowing AI and computer vision to move to the edge. And that's what Rajesh has been mostly talking about. So for me, I'm just a happy user of it. You know, whatever they can give me, I'll take it and then try to create solutions of vision that can be deployed on the edge. So I would primarily talk about these two aspects there, and only as a use case I would, or as an example, I would pick up research that has happened in our labs. You can go beyond it, of course. Okay, so let's get back to computer vision. Okay, computer vision running on the edge, and we are talking about AI and smart cameras. So where does this whole story start? The oldest, dumbest model of camera, which actually acquires an image from the outside world, was this camera obscura, which is nothing but a hole in a room and light from outside forming an inverted image on the wall. You might have seen some of these happening in some of the ancient monuments that even there in India, you see these kind of phenomenon happening, and people used it, converted this into a box with a small hole here and a mirror here so that the image is formed and you can actually draft on top of it and create images. So that is kind of the oldest form of cameras that you can think about. At some point, people said, instead of hand drawing it, can I put some chemicals which react to the light? And this is apparently the first ever photograph that was captured in the world. This took a long while. I think took about 4 hours to capture it. It's on a plate in which some chemicals were coated, and it was exposed for 4 hours. You can hardly make out the outline. This is an enhanced version of it. It's a building. It's from Joseph Nipi's his house window looking outside, some roof of another building and tower and stuff like that. It took a long while, 4 hours, just to even create a picture like that. So this is, now we have gone to a place where instead of a human being looking at the picture, it's a chemical that is capturing the picture. And of course, from there, it moved. By 1957, people started thinking about, images as digital images. Of course, digital cameras did not exist. It was a physical picture that was taken, scanned, and scanners did not exist. So they had to create something with, scanners made of LDRs and so on. And this was pasted around a drum and then used that to do scanning. Very high resolution, 176 pixels by 176 pixels, the first one. But yes, still a picture. 1957. By 1975, Kodak had made the first digital camera. Now the light is falling on a light-sensitive array of pixels, and it's capturing images. So now we have, by 1975, we have reached a stage where digital images are now captured. Okay, so that's where the story starts. But now, if you look at it here, see where it is being stored. Some of you might recognize the storage device sitting there. It's what we used to have as an audio cassette. So it's actually written in digital form onto the audio cassette. Okay, but modern cameras have moved a lot from here. So this is just to set the context as to how much time it took to get to a digital image. But from there, in the last couple of decades, things have moved much more. If you take a current digital camera, it has significant amount of computing going on inside it. It's not just light falling and then captured. There is a lot of processing going on. A basic camera still does, you can think of it as there is some illumination going on that would illuminate the scene. And then the light that is reflected back is being redirected by this optics into a sensor that is inside here. And that sensor would read out a set of numbers, which is slightly processed by the sensor. And then finally, it results in an image which might look something like this. So this is the basic story. But what happened is that over a period of time, people realized there is a lot of things going on here. If you can improve that processing, lot of issues that are there in the sensor can be corrected. There is sensor noise, which can be filtered out with some of the classic filtering algorithms. That was done. Next, somebody said, there are issues with the optics. I can do some corrections, distortion correction of the lenses. I can take a fisheye lens and make it rectilinear using processing that is happening. So slowly, the sensors, the processing from the that is happening after the sensor started increasing to the extent that you have now full-fledged computers living in your dedicated digital image, digital cameras. And of course, your cell phones have got significant amount of compute that you have just seen. Okay, so modern story is that this is, if you take it out, there is a lot of computing that is going on inside. And then computer vision researchers started asking, we are working on this problem. We capture images using our digital cameras. I'm sorry, I pushed something out. What happened? Okay, somewhere here. Something went wrong there. Okay, that's good. So we said, our goal is to take the image that is coming out of the sensor and do processing. And since there is already a powerful computer sitting in the camera, why can't we push some of those algorithms onto the camera? And that's where this whole field of computational photography that was born. Okay, and computational photography said we can modify this process anyway. If the output is anyway going to be processed, if what we are looking at is not the real image that is formed on the sensor, we are going to process it anyway. Why do we insist that what is formed on the sensor should be like a normal image? We can afford to freely change anything during the capture process. As long as we can do the post-processing to bring out an image that is useful for you, that's good enough. And that is even more important in computer vision, because for computer vision, the consumer of the image is not you. Many times it's a computer, which is actually trying to recognize what is going on in the scene. And if that is happening, for the computer, there is no requirement that the image that the computer sees should be like the image that you see. In fact, many of the animals in the world does not see images the way you see. They have things like compound eyes, where parts of the world are seen by different eyes and the brain puts those things together. Even we do that. We have many times we don't realize when we look at somebody, there's a big hole of seeing nothing right in the middle of where we are looking. We never see that hole. Your brain interpolates and fills it up. And we think we are seeing a nice clean image. In fact, what we are seeing is a very low resolution image of this whole world, where there is a small portion of high resolution that I can see. And then just next to it, there's a huge black hole. That's the actual thing that is going on in our retina. But our brain is processing it to fill up all those things. We look around, our brain is stitching together everything that we see around and make us feel that we are looking at a high resolution image. So our brain is anyway playing this trick on us. So why insist that your camera should be uniformly high resolution and so on? We can play around with that. We can play around with the illumination if you want to. So for example, I can try to throw some complex illumination onto the scene if it is useful. In some cases, it is useful to throw non-regular illumination onto the scene. And once you capture it, the optics need not be regular optics. People have shown that you can actually take a bunch of glass pieces, crush it together, put it into a box and send the light through it. It would go through some complex pathways, but as long as I can reverse that in the computation, it's okay, it's doable. Why is this of interest? Well, if you have a situation in which the optics is not functioning properly, you can actually reverse the consequences of it. This is what happened in the case of Hubble's telescope. When it was sent up, something went wrong while the manufacturing of the glass. It did not work properly. The shape was not appropriate, but people were able to figure out what was the final shape and then re-engineer the original image out of it. So that is also possible. So computational optics became a popular one to modify the optics to do interesting things. Computational sensors, the sensor itself need not be a simple array. You can have more complex things going on there. And of course, the processing that is happening afterwards. So putting all these things together, you can come up with an image like this. that might be one output, but maybe if I can do all these changes, you can also do things like create a 3D model of the world that you see, or create stereo images and so on. Okay, so this is the complex setup there. You have illumination, the scene, the optics, some detector, the sensor, picture coming out, some computation happening on top of it. And finally, what comes out can be called as visual intelligence. That's the high level thing. It's not just the image, it could be far more than that. So that's what we think of it in computational photography, the high level picture. Now, why is this interesting in our context of vision on the edge? Because number one, it requires computation on the edge, number one. Number two, I can use the story to improve my visual intelligence. What we are talking about in visual intelligence is this computation here, to come up with some interesting output, to recognize the world, to create a 3D model of the world, many applications like that. But if I'm trying to do that, maybe there is scope of modeling all these other aspects and modifying those other aspects, like illumination, like optics, or the sensor, to improve the final outcome. So if I want a self-driving car, maybe what you need is not just a simple camera, but something else. Okay, so that's the whole story. So we'll look at one example in which we looked at that. So this is a classic example before the modern modern AI started. We try to do this. I work in this field called biometrics, recognizing people. And one thing what my student did was to take the hand. This is trying to recognize you from the hand geometry. And from an image, you can recognize a person from the back of the hand. But we figured that if I just throw a bunch of light, structured light on top of your hand, it's not just the hand geometry that you can recognize in terms of the 2D shape of it, but I can actually capture the 3D deformations of the structured lighting, which indicates the exact 3D shape of your hand. And using that, I can actually come up with a recognition of this thing, which would actually significantly improve. So there's some standard image processing and feature extraction and so on going on. And these are showing the results of the recognition. Ideally, you should have this curve going like this. So there are two kinds of errors. You can see this, false acceptance and false reject in any kind of two-class classification problem. This is like you being recognized as you, or you being misrecognized as somebody else is one kind of error. And then you not being recognized as you is a second type of error. So those are the two kinds of errors, which if you plot here, you can see that the state-of-the-art methods over there in 2D is somewhere here. Whereas when we just throw in the light, suddenly you see a significant improvement in terms of what you can do. So this is just by pointing out that, if you have an application in mind, maybe there is scope for modifying things beyond just the output of the cameras. So this, took the error rate from 4% down to 0.8% at that time. So this is quite some time back. But this kind of work that what we just said, this is basically trying to do some illumination changes, but there are several innovations in vision that is allowing AI on the edge. And one such work I would like to start with is in terms of omnidirectional imaging. So suppose I want to have a camera that not just sees a close region of the world, I want to see all around. If I want to have an intelligent machine that is operating in the world, it is useful that if the machine can see not just forward, but all around. This is common, let's say, in something like a autonomous navigating robo or a car. It's useful to see everything that is going around. So there are cameras that can see all around, multiple cameras that are pointed in different ways, integrating the images together to get that. That was one solution. There was other solutions where you can take a bunch of lenses and mirrors and have a single camera that can, capture light from all around the world directed into the camera and then get a 360 view of the world using a single camera that is possible. So this is one work that was done by one of the famous computer vision researchers, Professor Sri Nair from Columbia. He used to sell these cameras, which captures these images. The images finally looks like this, but since there is computation available afterwards, I can take that image, de-warp it, and convert it into a 360-degree image. Okay, so what we asked is, okay, this is good. I can see all around, but if we want to get human-like intelligence, we want to not only see the image around, I want to be able to see it in stereo. So I want the left and right eyes of the view of the world from in all directions. Okay, so we asked, how can we do that? The problem there is that if I want to look around, I'm basically looking about turning your head around, assuming you are turning your head around this axis. What you're seeing is the view from two cameras. So one camera here, the second camera here, the left and right eye views are two cameras like this. The problem is that the moment I want to turn around, your cameras will be moving around in a circle. So if you imagine it, you will have your left eye view, left eye camera, which is looking forward. Assume that you are looking at the head from the top. Your left eye is looking forward. And when you turn around, you will have a bunch of, the camera would be moving around. Okay. And what happens to the right eye? Right eye is also similar. Right eye was over here. That will also move around. So you will have, if I want to capture 360-degree stereo, I want to be able to capture all the images that is seen by all these left eye cameras and all the right eye cameras. But it's even more complex than that. The problem is that I've drawn it as two different circles, but when you rotate your two eyes around, it's around the same circle. So these circles are actually concentric. That means the right eye cameras will be sitting like this. I want to arrange a set of cameras that are sitting in a circle. And then I need a bunch of left eye cameras which are also sitting on the same circle. And these cameras will obstruct each other. So it's not possible to create a 360-degree stereo by arranging a set of cameras in a circle. That wouldn't work because essentially each camera would be seeing the back of the other camera. And then there'll be other set of cameras which are facing, you can't even place them together. So people came up with some clever solutions. One solution was that you put a camera not on the circle. I want to capture the images on the circle, but put the camera out there and then simulate the view that you see from these two cameras using the image that is captured by that camera out there. So you take strips of images from this camera and that would, you can show that the strip of image over here can be kind of approximate the view that is seen by this camera and another strip of image here, which would approximate the view by this camera and so on. Okay. So you can do that. And then what do? You put a bunch of cameras around in the circle and then take pieces of these things together and combine it to create the 360 stereo view. Okay, and people did create this. Famous companies came out with solutions like this. You might recognize things from Google, Facebook. All these people came out with cameras that look like this. They were quite expensive, some 15 to 17K, 30K, and so on and so forth. And vision on the edge was not possible because these Facebook actually had put the software also in open source, and it took about 30 minutes on a cluster of servers to stitch together the images for one frame. So if I capture images using this, I say 30 frames per second, every frame would take like half an hour to rebuild into a full resolution image. So the problem is that the computation required is so heavy that you can't put it on the camera and get a feed of this 360 stereo. So here is where we asked, can we look at innovations in computer vision to enable vision on the edge? Can I compute everything on the edge, but do some intelligent capture, modify the process of capture, modify the optics maybe, and see if I can create a 360 stereo. So what we did is something like this. So we essentially wanted to do it. Okay, so we tried to push the optical edge there. We took this same configuration, but instead of capturing this using a single camera out here, I put two mirrors here, which would deflect the rays of light which were to be captured by these two cameras into a third sensor, which is sitting here looking down there. Okay, so we created a set of what you call as catadioptrics. Catadioptrics is a combination of mirrors and lenses, which would actually simulate this thing. So two mirrors which would take those two to capture the equivalent of these two cameras, then do the same thing for this view, take another two mirrors here, which would reflect those two views and so on and so forth. You keep doing that for everything together, you end up with a optical structure which looks something like this. That's just to get a high, simple idea of it. it, if you look at it and go beyond, there's a lot of optical engineering required to get to it. Finally, we got into a shape that looked like this. So this shape, this is actually the shape of a mirror. All the outward surfaces that you see are reflecting surfaces. And you put a camera inside here, which would capture all the parts of the mirror from here. The final product that we created in the lab looked like this. There was a camera sitting here, and this is the mirror that we created. We had a second mirror, which would, so that the camera can see the mirror. We kind of folded the optical path to make it smaller. This was able to actually capture all the images required by that set of cameras that you saw from Google and Facebook. Not just that, the design was in such a way that we did not have to do the stitching. The stitching that was required by those cameras was required because the cameras was placed at a very large circle. Here, all the images are being captured from very close to where it should have been captured ideally. So in that case, the stitching becomes a simple mapping from the captured image to the final one. So we are able to now capture 360-degree. This is monocular 360. It was from one of the first cameras. Our current cameras can do much higher quality than this. And now that you also have stereo, both left and right eye views, I can compute the depth of the scene. So I have a camera that can capture 360-degree stereo with depth computation. All that can happen 30 frames per second on the camera with a computing power that is far, far less than what is there. Okay, so this would enable several solutions like this. You can do this is going on top of robos, which would capture 360 stereo, recognize people, avoid obstacles, all this kind of stuff. It can also do VR kind of applications and also surveillance. So this is the basic story. So this is how innovations in the vision could actually push some of these applications on the edge. I would quickly point out a couple more applications and then wrap up. So in addition to the stereo, there are several other use cases, other potential knowledge sources that can actually improve this vision. And things like prior knowledge, ground plane estimation, motion parallax, several things that we use to understand the world. How can we push those things onto the edge? Thanks to companies like Qualcomm, they have created nice computing machineries inside here. So we are now able to push not just this depth, but also things like semantic segmentation. I can recognize all the different parts. I can recognize people, ground planes, floors, all this kind of stuff. They can estimate the regions where the robot can navigate. All this can be done on the edge device with like 5 to 10 watts of computation power. It can run on the robot. So it's a very efficient thing at the end of it. We have gone through, this was our first camera that we created with my student Rajat there. And we have gone through several iterations of re-engineering it, improving it, doing all kinds of stuff, improving things like the mirror design, the molding, the coating, enclosures, camera design, sensors, the compute inside the device, the interface, manufacturing, testing, whole bunch of stuff. So he started a small startup which actually does this. A group of people who have pushed it now, which has now resulted in these 3 solutions. Actually, 2. One is this is the main camera, which has been now pushed down. There's even a smaller version and also a multi-camera solution, which actually works for these kind of applications, mostly for intelligent spaces and mobile robots and so on and so forth. And it can do all kinds of things, semantic segmentation, depth, navigation, 3D reconstruction of the whole world, whole bunch of things that are possible on standard platforms, running locally on the edge. So this is where we have taken an idea, tried it out, improved it, implemented it, published it, converted to a company, has been on it for the last 6-7 years now, which has reached a level where now it's being used by other companies to put this on their robots. Okay. So last point I wanted to mention is like we also did some of the work that actually Rajesh mentioned in terms of improving the efficiency of algorithms to be able to run on edge devices. One of them he mentioned is quantization. So quantization is when you're trying to take a floating point number down to a int32 or int16 or even smaller. If you take to the extreme, it's called binarization. So every number inside is either just 0 or 1, or 2 numbers. Need not be 0 or 1. It's usually plus alpha or minus alpha, so a positive number or a negative number. So if you take it to that extreme, you can still show that most of the networks work really well, except for a couple of issues. So most of them, they try to do that. We try to keep some of the layers of the network as not binary, but most of the networks most of the layers of the network as binary, and that actually improved the accuracy quite a lot. We show that just by keeping a couple of layers as non-binary, you can actually get a huge improvement in accuracy. We also did extend it to ternary networks. So you have plus alpha, minus beta, and then a 0 in between. So if you optimize the whole algorithm to have 3 numbers where one number is 0, and if you optimize it, what happens is that whichever edges which can be 0 is going to be thrown out. So you're actually integrating pruning and binarization together into a single framework, and you can optimize the whole network based on that. And here are some pictures of which layers can be retained and which has to be removed and so on and so forth. Okay. And we also did some work on what you call as efficient network design. Instead of trying to train a network and then try to prune it, can you? So the typical method is like this: you train a network, you prune it, your error rate goes down during training, and then it goes up, and you repeat the process. You repeat it, train, prune, and then keep on doing that. This is what people typically do. We try to look for some quick methods where you can actually go from here to here directly and then train in one shot. So you pre-prune and then train so that even the training can become more efficient. But how do you prune it without training is not something that is obvious. So we have to bring in some theory that is coming from the graph theory called expander graphs, which has certain nice properties. So we use the knowledge that is there in computer science, now trying to improve the AI, which is then trying to improve computer vision, which can be deployed on the edge. So some nice properties of expander graphs can be made use of, and you can show that there is significant reduction in flops possible with even hardly any reduction in accuracy. Also did some work on modeling performance on the edges so that you can predict if I have some networks which is giving certain accuracy, what should be, if I have a target accuracy, what should be the model size in that architecture so that you can figure out for a particular application how big a hardware do you require for that purpose. I'll wrap up with that. The last point I want to mention is something that is slightly playing the devils here. There's a lot of work that we do in biometrics, where we try to improve the security and privacy in biometrics sources. And one of the things that we do is try to catch hold of people who are trying to do what we call as presentation attack. So you present a picture of a person or a mask or even video replay on a high resolution display to circumvent things like attendance and so on. Okay, so this can be done quite easily unless you have specific methods to capture it. So what we asked is the negative question: can we play the attacker here? Okay, what is happening is that the detection devices are actually using properties of the edge devices. The edge devices, which are the displays, the cameras, the printers, and so on, which are playing around to create an image, and then you're trying to detect signatures of the printer or the camera or the display device in the process. Okay, so what we did in this particular work here is that we created a neural network model which models the edge device, what is happening physically in the edge device, and then mount an attack using that model. And we show that it's possible to mount an attack on the edge devices in such a way that the properties of the edge devices are captured by the neural network. Using that neural network, you do what you call as a hill climbing or gradient attack. And using that, you can actually fool most of the system that exists in the world. The so-called best systems that are out there can be fooled, and you can do it up to some 80% accuracy. 80% of the time you can fool the system using this. So just to point out that things are not all hunky-dory, there are issues there, and maybe we need to actually think about how to deal with some of those problems coming up. Okay, so I'll stop there. Thank you. I've again took 5 minutes more than what I should have. So thank you for listening to me, and maybe, yeah.
Thank you,
Rajesh.
Professor Anup. I think I will call Rajesh on the stage as well. Please give them a big round of applause to both of them. I think very insightful presentations. I think we have some goodies for you. Okay. I think maybe Shashi can.
Yeah. Thank you.
Thank you.
Is there a picture required or?
So we'll, I know we are running short on time, but I think we have some time for Q&As. So we'll start from Q&A questions from the audience. If there are any mics here, Shika, maybe we can give the mics. There are some mics there. If anybody wants to ask any questions,
There is someone with the mic there, yeah.
okay. I think
Hey Rajesh, thanks for the nice presentation. Thank you, Professor, also. So question to Rajesh is that on an edge device, you said we have multiple processing units, CPU, GPU, NPUs. For a given model and use case, can I actually split them into each of them in parallel to run it even faster? Or do I need to always select one of these mode to get this job done?
Yeah, it really really depends on how you deploy it. You could actually split your workload and actually run them in parallel. But I guess the key thing is it also depends on whether your software stack is capable of doing it. But in theory, yeah, you could actually take it and deploy it.
Thank you, Professor Anup and Rajesh sir, for very insightful and gripping sessions. It's very exciting to see that the Edge AI is getting to mainstream. While that happens, it's also imminent to ensure that the security and privacy are paid attention to. So, Professor Anup, this is a question for you. You have done extensive research on biometrics, computer vision, and AI. And through some of your recent IEEE publications, specifically on the unified model for face with the fingerprint authentication, the secure iris authentication, and the recent one on the ADV ADV Gen last year, you very clearly presented that the one that you are referring in the last slide, that adversarial attacks can be launched against the presentation attack detection systems itself, which is very scary and which is very concerning. So considering that, I would like to hear your perspective on the real readiness of Edge AI for the mainstream from the security point of view. Are the security defense mechanisms evolving, keeping up the pace with these kind of attacks? If not, where are the gaps? I know that the security research community and academia is paying attention, but is the industry paying attention? Where are the gaps? You would like to hear.
It's actually pretty good. Yeah, good. Thank you for the question. So it is a very important aspect that, when you try to deploy these things on the edge, the security and privacy is kept in mind when you try to develop solutions. One good thing about edge computation is that it's actually much better for privacy. So it's much better that my data resides on my phone and it's not sent off to a cloud for every movement that I do. That's one thing that is good. So I would really advocate AI on the edge, because that would significantly reduce the amount of privacy concerns for sure. And we have also done some other work on this distributed AI computing, which would reduce the impact on privacy. But security is a different story. And security is always this cat and mouse game. You would always have attackers who are trying to improve their attack methods, and then security researchers trying to defend it. And most of the people now agree that you cannot become just a defender unless you know how to attack. So if you want to learn to defend, you need to learn how to attack also. So this work was basically trying to do that, to see if how to learn to attack. And we already have solutions to prevent this. But the point is that the solutions that were created without thinking this attack can fall prey to those attacks. Okay, so yes, it is important to always keep pushing this up. There is a group of people who argue that the best way to do security is not to reveal the algorithms so that you don't know how to attack. I disagree with that. This is what in security is referred to as security by obscurity, and doesn't work very well. because the moment there's always some leak that happens, the information gets out and then your systems get compromised. So it's always better to develop secure systems out in the open where you know what the threats are. And more importantly, when you create systems, you can always think of fallback or backup mechanisms that can take care of such attacks, because you know those attacks, they are out in the open. So yes, it's an important concern, but at least AI on the edge is taking care of some of those aspects. It's primarily in privacy, but also some in security. I don't know whether you have something to add here. Any other questions?
Hi, thanks, Professor Anup and Rajesh, for the presentations. This is Imtiaz. Actually, regarding 360 view cameras, do you have any present use cases or future use cases which will be deployed or working on? So
this particular one that I presented is on, it's actually a company that is actually producing those cameras. They are selling it. They are being deployed on primarily mobile platforms. So mobile robots which are going around doing things like floor cleaning or disinfection. There are several such use cases where warehouse robots which are moving around to do movement of objects within the warehouse. These cameras are being used as the sensor to do both navigation and obstacle avoidance for those things. So yes, that is the primary use case for which we built it. The resolution, the speed were all focused towards that kind of use case. There is a second use case which going to the larger camera is going to go, which is for VR, virtualized reality, where we are going to deploy these at certain places, and you can put on these virtual reality devices like the Apple something recently they have announced, or the Meta Quest 2. A few things are there which are actually able to visualize things. So you can sit here and see how the world is like from a different viewpoint. So the example that I used to give is that I can sit inside the stadium while the cricket match is going on and look around and see what's going on live in 3D, 360, and so on and so forth. So there are several use cases for it, but primarily for this particular company, it's focusing on robotic navigation use case.
Hello. So yeah, this is a question for you, Rajesh. So you were mentioning that even large models can be run on the edge. Like, I mean, that's the goal. So when it comes to a particular neural network, what is the maximum size? Let's say, for example, large language models. What is the maximum size of the parameters you think can be run on the edge before the token rate becomes too small for for it to be viable? And also, like, in the future, how would it evolve? Like, would the hardware get even faster to support like even bigger models, or would it be like you would imagine that the same accuracy can be achieved in the future with much smaller models as well? Like,
I think it's a combination of things. Like I was showing in my slides, about 14 months ago when we started off, it was basically stable diffusion, 1 billion parameter that was actually running on the device. Right now, we have models up to 13 billion. So in about a year, we've actually gone multifold in terms of the number of parameters that we can support. But again, is it going to keep continuing at the same rate? I think that we would have to see. But essentially, it is going up. But again, at the same time, like I said, your model doesn't necessarily have to become bigger and bigger. We are seeing smaller models also becoming a lot more efficient in terms of what use cases they can actually enable. So I think it's going to be a combination of both. So the model size is going to come down. It doesn't necessarily have to be billions of parameters, right? Maybe hundreds of billions of parameters. At the same time, the number of parameters that you can support on the device based on all of the improvements that you saw, right? In terms of the algorithmic improvements, in terms of the hardware related improvements, that is also going to go up.
Give the mic there in front.
Thank you. Short question. One of your slides, when you covered the platform, Rajesh, You used the word hallucination along with the algorithms. I'm sure some of us did not catch that term in the algorithm context. So if you can just elaborate that.
Yeah. So essentially, when you talk about that, a lot of these algorithms, the key thing is it can really start to make up things, right? And how do you really ensure that is really not the case? That is essentially that was the reference.
We'll take a last question. I think back there, you can give the mic.
So good evening, everyone. I'm Anusha, like student entrepreneur. So I have a generic question regarding integration of nanotechnology and electronics. Like, what is the future possibility in this field? Like, what's the scope in this field? And like, is Qualcomm already into this, area?
So I think, okay, then, maybe if I can interpret your question, nano electronics. So I think broadly speaking, actually, there is a miniaturization happening on the silicon side. As you know, Qualcomm works as a silicon company, and we continue to use the smaller and smaller nodes. So I don't know if that's what you are referring to. I think, for example, currently we are working with 3 nanometer version of the silicon, which is kind of, really a nanometer kind of an area. So all the chipsets that Rajesh was talking about for AI, we need to get to smaller and smaller transistor size for it to fit these large language models, because you need to pack a lot more information in a smaller form factor to give the power advantages and to have that scale. Because say if you want to have so many billions of parameter kind of model running on a small form factor device, we need to continue to miniaturize. So you are going to see that trend. So currently we are in 3 nanometer. We are going to see a 1 nanometer in sub 1 nanometer as well as we move forward.
Thank you, sir.
Thank you.
I'll just add one line to that, say that what he said is about nanotechnology for devices and AI. There is also the reverse of AI being used to improve the nanotechnology, and there's some research going on in that, in trying to, at least in IIIT, there is some work on trying to use nanotechnology for other applications like, medicine and so on. But a lot of AI is actually being used to improve the nanotechnology itself. So that's another interesting line.
Okay, thank you. Thank you, Professor Anup. Thank you, Rajesh. I think thank you for all your questions. So I will hand it over to Professor Ramesh.
Thanks, Rajiv. Thanks, Anu. So we'll just a little bit of the next slide. So we have, like I told in the beginning, we're going to be kind of capturing these thoughts from the talks a little bit, quite in depth, and then we have 4 other features. So we said we'll do a dispatch every month, right? It'll be like I don't want to call it a newsletter. Newsletter has a very fleeting view. It's a of 6 features relating to this topic, 2 from the talks itself, and then 4 more. With the 2 from research, 2 more, 2 directly from research. There'll be some research work being talked about. Then we'll have 1 from industry, more around use cases and such. And we'll try to get 1 global view, somebody that has a broader view. And so the first 3 we'll always do. The global view, if you find somebody this time, Professor Bhagwan Chaudhary found a professor from ISB who was a nice view. So he's doing the 4th feature. So there are 6 features that will be in the dispatch, which will come out first of the month, following month. So the first dispatch will come on July 1st. So next slide, please. Let me just quickly introduce. We requested the leaders that are contributing to the next edition. So if I can request Janakam to please come on stage. And I think Suresh Purni is here. Professor Suresh Purni from IIIT and Professor Karthik. I think Suresh had to leave, I think, here another engagement. And Manish from ISB couldn't join us today. So I'll just let them just quickly introduce their feature in a minute or so. The idea was they're here so you can talk to them during networking because they have some very interesting viewpoints on this topic, AI on the Edge. Jani?
Thank you.
honored to be a part of the very first dispatch. So my name is Janakiram. I'm a market research analyst and a hands-on practitioner. So the idea that I have proposed through this article is using large models, large language models on the cloud, which are capable of performing reasoning, performing very complex breakdown of the prompts and the tasks, and then using a small language model at the edge on a fairly low powered device. So the idea is when you actually send a very complex prompt without the data to the large language model running in the cloud, something like a GPT-4o, the job of this large language model is to take this problem and break it down into multiple tasks or prompts, which will flow back to the edge. And the edge, which has access to data, it has all ears and eyes to the actual data running within the environment. It can act as the proxy for the large language model running in the cloud and can perform the tasks and the execution as suggested and as directed by the large language model. So when I first echoed this to Ramesh, he gave me this idea of the data not being shown to the model not seeing the data. So how do we proxy this without sending confidential, compliant, private data to the cloud, but yet take advantage of large language models? So this is a federated LLM architecture where we have a proxy model acting as a small language model working at the edge, basically taking the instructions coming from the large language model and executing on behalf of it. So that is what I have proposed in this paper, in this article. Thank you.
And Karthik, if you could quickly introduce the feature you're writing.
Yeah, first of all, good evening all. It's an absolute honor to be here and fantastic organization. So it's great to see you all here. So my name is Karthik Vaidyanathan. I'm an assistant professor at the Software Engineering Research Center, IIT Hyderabad. So I work in the space of software architecture and machine learning, something in between them, right? So where my dream always has been like, can you build softwares that can automatically fix themselves, right? Softwares that automatically understands that they are having some issues and automatically fix themselves, something that goes in the line of that we call as self-adaptation. Now, on the edge, this becomes even more important and interesting, right? So you have different types of machine learning models that are deployed on the edge. So can you come up with a mechanism that can allow system to understand there is some problem going on and kind of fix themselves? So as a first step, what we did is we said, what if you have multiple machine learning models and you kind of come up with an approach which allows the system to understand the context and then switch between multiple machine learning models? For instance, if I am putting a camera here, as Anup was mentioning, right? If I put a camera here and I count number of people using some kind of computer vision algorithm, I might need a very good algorithm that can detect how many people are here. But if this hall is empty and there is a camera here and it has to run an algorithm, I can simply run a lighter model which does not require much computational power. So can I now switch between the models, understanding the context so that my system can offer a better quality of service? So this is what we have been working on, and we kind of deployed it in the QIDK kit of Qualcomm, and we got some amazing results. So with that note, I will leave you so that you can read more from the article, or I'm here, so feel free to chat with me. Thank you.
The QIDK kits is in the Qualcomm. Qualcomm has set up an Edge AI lab. Thank you, Rajiv, Sashi, and others for the Edge AI lab that's being set up at the campus, and the QIDK work is happening in that lab. And Suresh is writing about, they do a lot of work. There's a computer systems group. They do a lot of work in optimizing algorithms for the edge. So that's his feature. He's taking one of the works, research work that's happened there. And Manish from ISB is broadly what's happening in globally, like what are, it's just a lay of the land feature coming from taking a lot of references of what's happening. So those are the 4 features, in addition to the 2 features coming out of the talks itself. So thank you so much, Janagram and Karthik. Please feel free to talk to both of them. They're here during the networking. And before we just, thank you. So before we switch, next slide. So we have a steering council. I did mention, refer to the steering council at the start. We said this is a cities. We'll get few more. We're trying to get a professor from IIT, probably the Dean of Innovation there, onto the council as well. And but the idea was to have industry and academia together curate this. So we have Professor Bhagwan Chaudhary from ISB already on it. And then, so we have Sashi. You already met with Sashi. Sashi of Qualcomm is on the council. Let me just introduce Alok. Alok, please. You can just come up here just so they know who you are. Alok heads Goldman Sachs in the city, and we've been doing a lot of good work with them. And of course, Goldman Sachs does a lot of good work anyway. So we're happy to have Alok. We thought we'll just try to get different perspectives. There's Microsoft, Google, and Saj bringing the software product perspective. There's Qualcomm bringing the hardware software, like PJ had said, the boundaries are getting blurred these days. So it's good to have Qualcomm. And then we have MSR bringing the startup ecosystem, that viewpoint, and Professor Bhagwan Chaudhary bringing the business school angle. And we have Srini and PJ from our board are kind of guiding us as well in this. So the steering council is kind of helping curate the structure. I mean, last 3-4 months we've been meeting, help curate the structure of the whole series. And like Pijan said, we want to make sure it's easy to start. How do we sustain, right? It shouldn't be a flash in the pan just where it happens just once or twice and then just fizzles out. So we did a lot of legwork. And this council also will help advise as we go through picking up themes. We already have the themes for the first 4 months. We'll continue to do that. So thank you to all the steering council members. And with that, thanks again to Sashi, Rajiv, and the whole Qualcomm team. And of course, to Rajesh and Anup for the wonderful talks. And please, we'll just move to networking, pick up some coffee or tea, and just have those conversations. Like I said in the beginning, the starting point for this series was to say, like, how do we trigger meaningful conversation between the industry and academia? Right, and those conversations are important to discover possibilities and of course take them forward into some possible collaborations and such. And so we'll get more of academia coming in from next month, and of course the industry will be invited anyway. So please, the conversation is the most important. Please let's move on to the networking, and thank you so much everybody. Thanks for taking the time. And thanks to Qualcomm.